Hi, I'm George, and here's another Double E video. So, this is another signals problem, and you can see here that we have a DT LTI system represented by this sinusoidal function here, and this magnitude and phase plots of our response function. So, as you know, with any kind of system, you put together the input and the response, and you'll get some kind of output, which in this case will be y of n. So, this problem kind of walks us through the steps we'll need to find our y of n. You can see that's the last thing it asks us for. It starts us by finding the fundamental period, n naught. Then we want to sketch our x of n, and then we'll find our Fourier series coefficients, which we'll then use to find our values of, or to find y of n. So this problem has, the last two parts of this are a little long. You can kind of take a while to get done. So what I'll do is I'll put some links here in the video that'll let you kind of skip forward if you aren't interested in seeing the first two and just want to get to the answers. Then just click on the potatoes. I'll put potatoes over here, and they'll take you to the answers. All right. So we'll start with part A. So we're trying to find n naught of. Let's go ahead and copy this guy. So copy and paste. Okay. So we know that this right here is our frequency. It's not our fundamental frequency. It's just a frequency of the function. So to find n naught, what we're going to do is we know that n naught, or I'm sorry, some value n is equal to 2 pi times the frequency, right? So basically what we want to do is we want to get this value here in some form that's 2 pi times some value, k. We'll just use k. So what we'll do, and this is an algorithmic way you can use to find any frequency given this, is you take this 2 pi over 2 pi multiplied by your value for omega. That's a 2. And you can see that pi cancels out. These become a 4. You end up with, let's see here, 2 pi times 5 over 4. And you can see that 5 over 4, that's prime, which means that 4 n naught equals 4. So we're going to need to find our fundamental frequency as well for later on in the problem, so we'll go ahead and do that now. But this is the answer for A. So if we want to find omega naught, we'll just take this fundamental frequency and move backwards. So we know that fundamental frequency is equal to 2 pi over omega. So that'll be equal to, or I'm sorry, 2 pi over n naught. Since n naught is 4, you just end up with pi over 2. So we'll come back to this later on. All right, part B. It wants us to sketch x of n. Now, we know if this was in the continuous time domain, we know that a cosine function would just kind of look like this, right? And it would go from 1 to a -1. But in the discrete time domain, the shape of a sinusoidal function depends on the things like the phase shift. So it's not going to look, it won't necessarily look like the function that we see here. We'll go ahead and start. So we want to be able to sketch this. The first thing we'll do, so what we'll do, we know that our fundamental period is equal to 4. So what we'll do is we'll choose values of n naught that are consecutive, and there we go. So we'll choose 4 values of n naught that are consecutive. And so we'll just plug these in for n. So if we go ahead and make a table here, and cosine 5 pi over 2 n minus pi over 4. Let's make this a little bit bigger, 0, 1. Start back, -1, 0, 1, and 2. Excuse me. So if we plug in a -1 into n here, we end up with a cosine of, let's see here, So negative 5 pi, that ends up being negative 10, so negative 11 pi over 4. And that should be a negative 11 pi over 4. And that ends up equaling negative square root of 2 over 2. If we put in a 0 there, it's just cosine of pi over 4, which is equal to square root of 2 over 2. If we put in a 1, that'll be 10 minus 1, so that's cosine of 9 pi over 4, square root of 2 over 2. And if we put in a 2, it'll be cosine of 19 pi over 4, which is equal to a negative square root of 2 over 2. So these are our 4 discrete time values that represent the entire fundamental period. So if we go ahead and see here, 0, or 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You can see that for a value of negative 1, we have a negative square root of 2 over 2. 0 and 1 are both positive square root of 2 over 2. We'll say that this value here is square root of 2 over 2. This value here is negative square root of 2 over 2. And so you can see that for a value of 2, we have a negative. And because this is our fundamental period, we know that, so over here we're going to have just a repetition of this. So bam, bam, bam. Same thing over here. So these should be taller. This is what we end up with. And you can see that this continues on for infinity in both directions. So this is our answer to B. And that's all. Moving on to C. So we want to find our Fourier series coefficients for x of n. And all that is we're looking for our values of a sub k. So part C, go ahead and paste this guy back in here. Now, we know from part A, right over here, that our omega naught, our fundamental frequency, is pi over 2. So we're going to take this and let's see here. So actually, you know what? Yeah, we'll go ahead and do it like this. So what we're going to do is we're going to take this cosine and we're going to split it up. We're going to split up the terms on the inside. So you can see that this is equal to n times 2 pi plus pi over 2 plus pi over 4, and that's a negative sign. Okay. So you know that inside of a sinusoidal function, a value of 2 pi, you just make it go away, right? Because it doesn't give you anything, doesn't give you any extra information. So you end up with cosine of pi over 2n minus pi over 4. Now, you can see that pi over 2, well, that's just equal to omega naught. So you can rewrite this as cosine of omega naught n minus pi over 4. Now, this math worked out in this case, but if it didn't, if you ended up with some kind of constant, like say, 3 times pi over 2, and then it would just be, that would just become 3 omega naught n. And that'll be important later on when we find our values of a. But so working from here, you can see that this, what we want to do with this is get it into a form that let's see here. So we want a Fourier series coefficients. We want to get it into a form that works with the Fourier series synthesis equation. And for discrete time, we know that the let's see here, synthesis equation for some x of n is equal to the summation from k equals negative infinity to infinity of some a sub k times e to the negative j k omega naught n, right? So we know what omega naught is. It's pi over 2 because we found it, right there. And n is a value that will just be a part of the function, and so we just need to find k and a of k. Now, the easiest way to get this function in that form is to do, and is to use one of Euler's formulas. Euler's formula, and that is that some cosine function is equal to 1/2 e to the stuff on the inside, which in this case is j times the stuff on the inside, omega naught n minus pi over 4 plus 1/2 times e to the negative j omega naught n minus pi over 4. So we'll go ahead and we're going to simplify this by breaking up this compound e into two separate exponential expressions here. So we'll have 1/2 e to the negative pi over 4 times e, and that should be a j in there, e to the j omega naught n plus 1/2 e to the positive j pi over 4 times e to the negative j omega naught n. So looking back up here at our synthesis equation, this right here is these values on the right of both terms. Our a sub k is simply equal to the first half of each of these terms. So and so, to find what values of k correspond to these values of a, you just have to look at the exponential term on the right here. So you can see right here, k essentially equals a value of 1. And over here, due to this negative, k is equal to negative 1. So we can say, and you'll notice that there's nothing, there's no constant, there's no DC value, so there's nothing for when k is equal to 0, and there's also nothing for when k is equal to 2. Because if you'll remember, we're working with a period, and we just arbitrarily choose this period to go from -1. Actually, no, because we're using the synthesis equation, we're looking at values from -infinity to infinity. So really, this entire summation from -infinity to infinity yields only two values for k equals -1 and k equals 1. So if we just look at this from the point of view of a fundamental period from -1 to 2, we can say that a sub k is equal to, and we'll go ahead and put an open brace here, it's a 1/2 e to the negative j pi over 4 when k is equal to 1, 1/2 e to the j pi over 4 when k is equal to -1, and this should be a 4 and this should be a j, and it's equal to 0 when k is equal to 0 or 2. So this is our answer to C. And you can see that it took a little bit of work to get here, but the only tool that we needed, the only part of signals that we used was the synthesis equation. And we got our Fourier coefficients. So what we're going to do now is we're going to use these to find the answer to D. And D is right here. It wants us to find the closed form expression for some value y of n. So if we think about this as in terms of an LTI system, we know that x of n convolved with h of n yields some value y of n. And if we think about it in terms of Fourier transforms, actually, you know what? We won't even need to worry about that. We're just going to look at this from the point of view of the synthesis equation again. So, looking at y of n, we can say that y of n is equal to, and we're using the synthesis equation from k equals -infinity to infinity, some b sub k, we're not working with a now, we have something new, times e to the negative jk omega naught n. So this is the same term that you saw as the answer to B. And so we're going to define b sub k as equal to our a sub k times some new value, which is the magnitude of h to the e to the jk omega naught times the phase, or no, not the phase, but e times the phase, e to the j of the phase of the h, to the e to the jk omega naught. So, what does this mean? Well, a of k is pretty self-explanatory. The second half of the term, on the other hand, is, so what this is we have our magnitude and we have our phase, right? And if you think about this, back here in the original problem, we had some expression of cosine of these values, and they were equal to, and we'll just use half of this expression here just to illustrate my point. Oop, undo. Okay, and so you can see right here that this a term is our magnitude, and this is our phase. So you can see that these two, I need to learn how to draw straight lines, don't I? Nope. Okay, so you can see that they're equivalent, and that basically what we're doing is we're taking whatever it is in our phase plot and elevating it to the power of e, because that's what we do when we're converting from our sinusoidal function to some other function, and it just, that's and that's how it works. So I'm gonna have to cut that. Coffee. Okay. Magnitude and phase. We got a magnitude and we've got a phase. And really, so really, just like the way we raised, our omega naught n to the power of e when we're working with the cosine, we also want to raise the phase response of our impulse or our response function to the power of e, just to give us, it's what gives us the correct values. So let's go ahead and start this down below. Let's see here. So we're working with b of k is equal to ak of all of that. So we're just going to say that, let's see here. Let's think about this. I'll just rewrite this guy. Give us a new line to work with. Okay. Now, starting over from here. So we already kind of know what a of k is, but we need values of k, and we need values for omega naught. Well, we have values for k and omega naught, right? So we know that a of k is only non-zero when k is equal to plus or minus 1. And for all other values, a of k is equal to 0. So what this means, since we have our b of k defined as a of k multiplied by these values, if a of k is equal to 0, everything is equal to 0. So we don't have to worry about, all we have to do is worry about values of k that are 1 and negative 1. So we can rewrite this as b of k is equal to this system where we have we'll start with a of 1 times the magnitude of h at e, j, and k is equal to 1, and omega naught is equal to pi over 2, times e to the j times the phase of e to the j, k, and k is also equal to 1, and omega naught is equal to pi over 2. So j pi over 2. And I forgot the frequency part of this. Move this guy over. H of. There we go. That makes more sense. So phase, or our phase and our magnitude. Now, the second half of this, -1, is the magnitude of h of e to the negative j pi over 2 times e to the j, phase response of h, e negative j pi over 2. So, because we have graphs of our magnitude and phase responses for our h function, we can just go ahead up to the top of this this page here and evaluate it, graphically. So zooming in, take a look at pi over 2, negative pi over 2. You can see that no matter where you go, anywhere on this line, you're going to have a value of 1. So that just equals 1. We can just go ahead and pretend that guy doesn't exist. And here we go. So you can see that right here, at negative pi, we have a value of pi over 2. At positive pi, we have a value of negative pi over 2. You can see that this function here is linear, between pi or negative pi and pi. So, it stands to reason that right here and right here, halfway between 0 and the respective ends, that you're going to have a value of pi over 4. And when your omega is equal to negative pi over 2, then your of e to the j omega h to the e to the j, there we go, is equal to pi over 4, and similarly when it's equal to pi over 2, you're going to have a value of e to the j omega is equal to negative pi over 4. So we'll go ahead and bring these values down to the bottom here. There we go. So we know that this equals 1, this equals 1, and this, because it's the negative 1, it's the negative value of k. We know that this is equal to, it was pi over 4, and this is negative pi over 4. And now, keep in mind, we're not getting rid of these j's, we're just replacing this function here with the respective pi over 4 and negative pi over 4. So, this equals a sub 1 times e to the j, negative j, pi over 4. This is equal to a negative 1, e to the positive j, pi over 4. And using, Euler's identities and whatnot, we know that e to the negative j pi over 4 is just equal to cosine. Oh, we don't want to do that yet. We haven't simplified a yet. So let's go ahead and at this point let's pull a in. Copy and paste. So instead of writing out a, there we go. So these are our values. These are the expressions of our b sub k. So you can see that you can simplify these exponentials. So let's go ahead and do that. You end up with 1/2 e to the negative j pi over 2, and this is equal to 1/2 e to the positive j pi over 2. Now we'll use Euler's formulas to simplify. You don't want to do it before you bring in your other constant terms, because if you do, then you might miss out on some easy simplification. So it would have worked out either way. It just would have been a lot more math if we had to do it again after bringing back our a sub k. So we know that e to the negative j pi over 2 is equal to, using Euler's formulas, cosine of pi over 2 minus j sine pi over 2, and this is 0, this is 1, so it just equals negative j. Similarly, this guy is equal to j, so b of 1 is equal to negative j over 2. b of negative 1 is equal to j over 2. So we have half our answer. Let's go back up here. So we'll go back to where we defined this. Now, I'm being technical here and saying that this is where k is equal to negative infinity to infinity. We know that because of the fundamental period that we've chosen, and the fact that a sub k, or in this case b sub k, is equal to 0, everywhere except for negative 1 and 1 within that fundamental period, we can just do the summation from negative 1 to 1, and then it'll just give us our two terms. So we can say that y sub n is equal to, and instead of writing b of 1 and b of negative 1, I'll just bring them down here. So negative j over 2 times e to the negative jk omega naught n. So that would just be, we already have omega naught, that's pi over 2. In this case, k is equal to 1 and n. Plus positive j over 2 e to the j pi over 2n. Let's see. That is correct. Okay. Now, this now we can simplify this a little bit further. Another one of Euler's identities is so we know that sine of, we'll just say this. We'll simplify this here. So what I'm going to do is I'm going to take this guy and I'm going to, let's see, I'm going to factor out the negative j over 2. And then I'm going to multiply everything on the inside by 2j over 2j. So, and then we have e to the negative j pi over 2n minus e to the j pi over 2n. Okay, so using Euler's identities, you know that this just becomes a sine function. So this then becomes, and let's not forget this over 2j. So we end up with negative 2j squared over 2, and the 2's cancel, sine, and this is just going to be, let's see, negative pi over 2n. And we know that, the j squared, any imaginary number squared, is equal to negative 1, so that'll cancel out our negative sign, and we just end up with sine of negative pi over 2n. And that is equal to our y of n. So it was a long road getting here. There's a lot of little steps along the way, but in the end we get this simple function. Let me go ahead and double check my notes to make sure we haven't missed anything. This is supposed to be a positive pi over 2. You can spend years memorizing this stuff, but it always helps to double check. Otherwise, you miss simple things like that. Okay, so does it ask us to graph it? It does not. But you can see what you would get if you graphed this. So now we have a function that is sinusoidal, but there's no phase shift. We're still in the discrete time domain, but there's no phase shift here. And so let's see what this looks like. So we're just going to go ahead, and our fundamental frequency is still 4. It stayed the same through this because we have the same kind of sinusoidal function. And so let's see here. We'll take values of n from -1, 0, 1, and 2. And we're going to have y of n on this side. So n of -1 just gives a sine of -π/2. That's -1. 0 is 0. 1 is 1. 2 is 0. And you can see what this looks like kind of in your head. Draw my lines. Okay, so -1 is -1. 0 is 0. 1 is 1. 0 is 0. And you can see this looks a lot like an actual sinusoidal function. And that's a part of what gets lost, or not so much lost, but changed when you go from continuous time to discrete time, is that the shape of your functions may be dependent on the phase shift, or just when you choose to sample them. And when you get to sampling, you'll see that your sample rate also has a huge impact on the shape of the discrete time functions you get when you translate them from the continuous time domain. So that covers how to solve this, and hopefully you found it as helpful as I did as a learning tool, and and good luck.